Magnetostatics, fields and currents. This will be a rather full lecture. We'll start off by talking about Maxwell's equations specific for magnetostatics and some of the consequences. Then we'll talk about one of the fundamental equations in magnetostatics, the Bio-Savart law. And we'll apply that to three different examples to try to give you a feel of how to use the Bio-Savart law. And then we'll generalize that to current distribution, surface currents, volume currents, and things like that. Okay, let's dive right into this. Maxwell's equations for magnetostatics. So we start with Maxwell's equations in the differential time domain form, and of course also the constitutive relations riding along with that. Now for statics, nothing is changing, so our time derivatives go to zero. And as we keep seeing, when we cross off or set frequency to zero, set the time derivatives to zero, Maxwell's equations separate into two sets of equations. And we just got done talking about the above set in electrostatics. Now we're moving on to our discussion on magnetostatics. So Ampere's circuit law reduced to the curl of the magnetic field equals the current density. This is saying that magnetic fields will circulate around currents. It also says that we will only have magnetic fields when there is a current. Just like in electrostatics, we only had fields there when charges were present. So here we can only have magnetic fields when there is a current that is present. We have our Gauss's law for magnetic fields. This is unchanged from electrodynamics. And it's saying that the divergence of the magnetic field is zero. So the magnetic field cannot appear to be diverging or converging to a particular point. That also means they can't start or end, yet they exist. So this means that magnetic fields are forming loops. And in fact, they form loops around the currents. We then have the constitutive relation that relates the magnetic flux density B to the magnetic field intensity H through the permeability. Notice the permittivity does not appear here, so the magnetic fields do not see the permittivity at all. In fact, the electric and magnetic aspects of a device are completely decoupled in statics. And to know everything about a device, we actually would have to do two different analyses, one as an electrostatics problem and the other as a magnetostatics problem. The Bio-Savart law. The Bio-Savart law is really derived from Ampere's circuit law. So Ampere's circuit law says we have a circulating magnetic field around a current, but it's really intended to calculate the current given the magnetic field. Well, what if we're given the current? How do we calculate the magnetic field? We have to sort of turn this equation around. And in doing that, that is the derivation of the Bio-Savart law. And we can do that for a line current, a surface current, or a volume current. The volume current is really the only physically real type of current. And so technically, I would have to say this is the Bio-Savart law, except we'll use it with the other line current and surface current because it's a great approximation to make. This is how I like to think of the Bio-Savart law. It's specific to the case of a thin wire, but that's very common in magnetostatics. And I'm expressing this in terms of a differential magnetic field. So the way this works, we have a wire carrying current I, and if we look at a little tiny piece of that wire, so it's a little tiny differential current element, it's in direction dl with length dl, and we multiply by I. So this IDL is our little differential current element. Well, our little differential current element induces a differential magnetic field that would circulate around it. And we can learn a lot about the relation between the current and the magnetic field just through this Bio-Savart law. So let's take a look at this. Well, inside the Bio-Savart law, we actually have a cross product happening here. And this has everything to do with the orientation of the current and the magnetic field circulating around it and where that comes from. So remember what a cross product does. It generates a third vector that is perpendicular to both of these vectors. That means the magnetic field we generate is perpendicular to the direction that the current is moving in, and it's also perpendicular to the vector which extends from where the current element is out to where we're observing it. So it's that cross product that really leads to this tendency of the magnetic fields to circulate around the current element. We also see this 1 over r squared dependence. So that's very much like in electrostatics when we looked at the field around a point charge. Now we're looking at the field around a differential current element, and we have the same 1 over r squared dependence. And that's because the energy is essentially spreading itself over the sphere as we observe it farther and farther away from the source of that current element. Due to the cross product, this is following a right-hand rule. So imagine we have a wire that's carrying a current upward, and we'll wrap our right hand around this so that our thumb points in the direction of the current. And when we do that, the fingers of our right hand are curling around that wire in the same direction that the magnetic fields would curl around the wire. So there's definitely a handedness in magnetostatics relating the magnetic field to the current generating it. Here that's a top view of the wire. Here's the wire, and it's coming in and out of the screen. And in this case, it's carrying the current out from the screen toward us. And so if you hold your right hand in front of your face and point your thumb at your face, your fingers will be curling in the direction of the magnetic field. But we can see that the intensity of the magnetic field decays with distance. And that is this 1 over r squared dependence. Notice that the magnetic field approaches infinity as we go to 0. And that's really because we're assuming that's an infinitely thin wire. And in practice, we don't have infinitely thin wires. The current is distributing itself over the area of that wire. And as we approach 0, we're actually ignoring a lot of the current, and the amount of current goes to 0, and we don't have infinite magnetic fields. That only happens when we assume an infinitely thin wire. But it does suggest, as we get close to a wire, that we do see the most intense magnetic fields. We can also look at the longitudinal dependence, just due to a little tiny current element placed right here. So we're not taking into account any of the current in the other part of the wire. We're just looking at the magnetic field due to a current element right at its center. And by the way, the magnetic field does not look discrete like this, sort of like a sliced egg. That's just the way that I'm drawing it. It's a smooth, continuous phenomenon. But what you're seeing here are the circles. If we were to turn this, you would see the circulating magnetic field. But here we can see the longitudinal dependence as we work away from our differential current element in either direction. And it approximately follows a 1 over z cubed dependence, which is different than the 1 over r squared dependence in the cross section. The other important thing is as we approach the current element in the z direction, it does not approach infinity in terms of the dependence in the longitudinal direction. And that's really because we have this plus 1 sitting here. Now, once we have this differential magnetic field that a differential current element induces, if we want to get the total magnetic field, we integrate that little differential magnetic field. So we integrate it over the length of this wire in this case, and what you're visualizing is the magnetic field around the differential current element. And so we're adding up all of these. And you can sort of simultaneously see the intensity in the cross section, the intensity in the longitudinal direction, as best as I can visualize. This is a really tough thing to visualize. So the total magnetic field is adding up all of those things that you're seeing as we integrate along the wire. So this is all best illustrated through an example. So let's calculate the magnetic field around a finite length wire. This, by the way, is very similar to an example we did in electrostatics where we had a uniform finite length charge. Now we have a finite length wire carrying current I. And we might ask the question, how can that wire carry current I if it actually ends here and here? Well, we're just going to mathematically pretend that it carries that current I and ignore that practical aspect of this. So we have our infinitely thin wire running along the z-axis, starting at position ZA and ending at position ZB. So to calculate the magnetic field, we will have to integrate the Bio-Savart law along the length of this wire. So we'll be integrating these little tiny differential magnetic fields along the length of the wire. So we plug in our Bio-Savart law and we set the limit so that we integrate from ZA to ZB. Now I like to write this in this slightly different form that I think makes the math a little bit easier. And so we have this ratio of our unit vector divided by r squared. I like this for physically interpreting the formula because it shows the 1 over r squared dependence. But for actual calculations, rather than have this unit vector in the direction of r, let's actually put the vector r in here, which means then we have to divide by r cubed to get rid of the magnitude up here. And so don't mistakenly think there's a 1 over r cubed dependence here. It is not. I just like this form for doing calculations. So the vector r, as we mentioned before, connects our differential current element to wherever it is we're observing the field. Now in this problem, our differential length dl is in the z direction. So it's dz in the z direction. That makes our vector r a distance rho in the rho direction and a negative z in the z direction. So our cross product, dl cross r, we plug in our expression for dl, we plug in our expression for r, and we work through the math, and we just get rho dz a phi. So we already see that the magnetic field will be in the phi direction, which of course is circulating around the current element. So we put that cross product back into our integral, and now we have something a little bit simpler to work with. We bring some constants to the outside. The current, the rho parameter does not depend on z at all. The 4 and the pi do not depend on z, and our unit vector in the phi direction does not depend on z. So we can bring all of that to the outside of the integral, and we're just left with this. So like we did for the electrostatics problem, we have this 1 over r cubed in our integral, which makes life a little bit difficult. So rather than integrate over z, let's integrate over an angle phi. This will require us to put everything in that integral in terms of phi instead of z. So here's the beginnings of that. So we were integrating from ZA to ZB. So to put this in terms of angle, we will integrate from phi1 to phi2. So notice what phi1 is. We have this projection from our observation point to the z-axis. That is at position z. And this line connecting our initial point of our integration is at an angle phi1 off of that projection. And then, of course, at our endpoint ZB, that's at an angle phi2. So our integral will go from phi1 to phi2 instead of ZA to ZB. And that's what we're conveying over here. Now the question is, what do we do with the dz, and what does this vector ratio become when we put things in terms of phi instead of z? So from the figure, we construct this triangle that I've shaded in, and we're looking at our little differential current element, and the angle that makes is phi. So we have a triangle that I've shaded in, and we have this angle phi. The tangent of phi is the opposite face, so that's z minus z prime, divided by the adjacent face, which is rho. So tan phi is z minus z prime over rho. We solve this equation for z prime, and then we'll differentiate that to get an expression for dz prime in terms of phi. So we differentiate, and we get this. Okay, now the vector r. Our vector r connects our differential current element to our observation position. So that is coming over a distance of rho, so it's rho in the rho direction, and it's going up z minus z prime in the z direction. So that's our expression for r. In the previous slide, we actually had a tan phi equals z minus z prime over rho, and if we solve that expression for z minus z prime, we get rho tan phi. Now what I'm going to do is factor out the rho. There's a common rho term. I'm also going to factor out a cosine phi. And the reason I do that is because we get a cosine phi and a sine phi, and at some point we're going to need the magnitude of r. And that will be very easy because the magnitude of what's in the parentheses here is just 1. So in fact, the magnitude of r is what we've brought to the outside. So it'll make that calculation a lot easier. Well, 1 over cosine is secant phi, so we can make it a little bit cleaner writing it this way. So the r cubed is really the magnitude of the vector r cubed, and this is very easy to do now because this rho secant phi is the magnitude of r. So that's very easy to write. It's just rho secant phi, all of that cubed. And that is because the magnitude of what's in here is 1. Okay, so we had an r cubed down here, which is now rho secant phi. But we still have our dz here, we still have our z limits, and we need to convert that over to phi. So now we integrate from phi1 to phi2. The constants on the outside stay the same because we're only messing around with our integral. But our dz, remember, is now negative rho secant squared phi d phi. So we've done it. Our integral is now completely in terms of phi and not z. We cancel our rho, our secant term, and we're just left with d phi over secant, and that's easy to integrate because the 1 over secant is cosine. So here's our integral. The antiderivative of cosine is sine. We evaluate the sine function at our limits and subtract. We then absorb the negative sign into the parentheses, and we end up with our final expression for the magnetic field around this finite length wire. Notice the 1 over rho dependence. That's not a 1 over r squared dependence. We saw that for our differential magnetic field. But in this case, we have our total magnetic field around the wire, and we only have a 1 over rho dependence. The direction of the magnetic field is phi. That means it completely encircles the wire. It doesn't have components in the z direction or the rho direction. It's only circulating around the z-axis. So even though our wire ends, if we're observing the magnetic field up here somewhere, it is still circulating around the z-axis. It's not pointing any other directions. Here's a quick summary of some of the points that we've already made. This solution is really applicable to any wire with a uniform current. It has to be a straight wire. The magnitude of the magnetic field decays with 1 over rho, not 1 over rho squared. And this is just like the decay of the electric flux around the finite line charge. And the magnetic field only had a phi component, so it forms loops around the wire. Our next example is the magnetic field around an infinitely long wire. This is actually pretty easy to do because we've already done the work. We can borrow the solution we got from the previous example and apply it to an infinitely long wire. We have the same setup. Now we have to think, when our wire is infinitely long, what values do we use for phi1 and phi2? Well, if our wire is infinitely long, this position ZA actually goes way down to negative infinity. That means this angle will keep increasing until this line is completely vertical. So phi1 is actually 90 degrees for an infinitely long wire. Now ZB for an infinitely long wire goes way up to positive infinity. That means this line will rotate all the way up and be completely vertical. Now phi2, downward is its positive direction, so when we talk about phi2 in the other direction, it's actually negative 90 degrees for an infinitely long wire. So now we can take our expression we got for the finite length wire, plug in those values for phi1 and phi2, and we'll have the expression for the magnetic field around an infinitely long wire. And there we are. We still have our 1 over rho dependence. It's still in the phi direction, and this is a much simpler equation. And in fact, even when we have a finite length wire, what we tend to do is assume that the magnetic field looks like this around the wire, and then that it's 0 away from the wire. And when we talked about the longitudinal dependence, it actually does decay longitudinally, and it disappears pretty quickly. So this is a very good approximation to make, and it's what we will do when we analyze magnetostatic devices. Now let's get a feel for these numbers. So suppose we have a 22 Aug wire and carrying 1 amp of current. That's a very typical wire we'd have in our circuit lab. So what is the magnetic field 1 centimeter from the wire? Well, we have an expression for the magnetic field around an infinitely long wire, and it's a nice, good, easy, clean expression, so that's what we'll use for our wire. We plug in the numbers. We have 1 amp for our current. We're 1 centimeter away, so this rho term is 0.01 meters. And we end up getting an answer of 15.92 amps per meter, so roughly 16 amps per meter. And it's in the phi direction, circulating around the wire. So 1 amp is not an unreasonable amount of current. For a circuit, that's pretty high, but not too unreasonable. So magnetic field intensity on the order of 1 amp per meter is what we tend to see around wires. Now let's generalize what we've been talking about to current distribution. So rather than just have a thin wire, now we'll be talking about sheets carrying currents. We'll be talking about volumes carrying currents. Our first current distribution is the point current. This is what we've already discussed. And we have a little tiny differential current element that we described with IDL, and it had units of amp meters. Because I was amps, the DL had units of meters, so overall we have amp meters. And we had our little differential magnetic field created by the little differential current element. Then, of course, to calculate a total field, we integrate over the length of a wire, and we did this and got a total magnetic field. Our answer was this. It was the total current divided by 2 pi rho, where rho is our observation distance away from the wire. And so we have a wire carrying current I, and along that whole length we have a magnetic field circulating around it, and the direction of that circulation followed the right-hand rule. Now let's take a look at a surface current. A surface current is confined to an infinitely thin plane. And so rather than use J or I to describe the current, a surface current density, we will use a vector K. So K will remind us that we are talking about a surface current, and it is a vector because the current is traveling in some particular direction. The surface current density has units of amps per meter. Now we need to take a look at our little differential current. It's a little area piece on this surface. And our little differential current in this case is K ds, where K is the vector quantity and this is a scalar differential surface area. And if we look at the units of this, we have amps per meter, and then ds is meters squared. Overall, our differential current has units of amp meters. What's interesting is our differential current for a line current also had units of amp meters. So when we want to calculate the total magnetic field outside of a surface current, we now integrate over the surface. And we have a slightly different form of the Bio-Savart law here, where we're integrating the surface current version that we talked about previously. Now let's use what we know to calculate what the magnetic field is outside of that surface current. So that means above it and below it. Well, there's two ways that we can calculate the total current enclosed in a particular line path that we choose on the left. One way is to integrate the current density over the width of this little window that we're integrating in. So we could integrate the current density. That's one way. The other way is to do a line integral of the magnetic field around this closed path. Both of these techniques should calculate the same total current. So in fact, we'll do that. We'll set them equal, and we'll end up with an expression for the magnetic field as a function of that surface current. So the first thing we'll do is integrate the magnetic field around the path that we're showing. And to do this, we're dividing that rectangular region up actually into 6 different integrals. So we will start at point A, and the first thing we'll do is we'll integrate from A to B. The next integral is from B to z equals 0. Then we'll integrate from 0 to C, then from C to D, then D to 0, and then 0 to A. So in all, 6 separate integrals. So we have our same picture, and we have our 6 line integrals. Let's go ahead and do them and talk through them one term at a time. So the first thing we're doing is we're integrating from A to B. That is in the positive x direction, and so there's a positive sign here. Now we don't yet know what the magnetic field is above that sheet current, but when we do a dot product in the x direction, what comes out of that is the x component of the magnetic field. And then, of course, the length of this integration is delta W. So it's the x component of H on the top, or above our surface current, times delta W. Then we integrate from B to 0. We're integrating now in the negative z direction, so we have a negative sign here. And when we perform the dot product, we only pull out the z component of H. And what is the length of that integration? It's delta H over 2, because delta H is the total height of the rectangle. We're only traveling along half of that, so it's delta H over 2. All right, then we go from 0 down to C. This point, it's the z component of H on the bottom. There's also a negative component here because we're integrating in the negative direction. And then the length of that line integral, delta H over 2. All right, then we integrate from C to D. That is in the negative x direction. So we have a negative sign here. And of course, that pulls out the x component of H. And the length of that line integral is delta W. Okay, then we integrate from D to 0. We're integrating in the positive z direction. So we actually have a positive sign here. Z component of H on the bottom, and the length, of course, is delta H over 2. And the last part of the integration is going from 0 to A, also in the positive z direction, so we have a positive sign. Z component of the magnetic field on the top, and the length of that line integral is delta H over 2. So that is our line integral. The next thing we'll do, in the limit as we let delta H go to 0, so those little rectangles closing in on the surface, the delta H goes to 0, and in fact, 4 of our terms drop out. And really what we're left with are just the line integral from A to B and C to D. So that's what we have. Now, due to the symmetry, this is a symmetric problem, and the fields always take on the same symmetry as what you're analyzing. So we would expect the magnetic field above and below this to look very similar. And in fact, the magnitudes of the magnetic field on the top and the bottom are the same. We can't say that about the direction, but we can say that about the magnitudes. So let's think about the direction. Let's pretend for a second the magnetic field above and below was in the exact same direction. Well, if they were in the exact same direction and these two terms were perfectly equal, we would get a 0 over here, and our total current would then be 0, which we know is not physically real. So the way that we reconcile this is that the magnetic field above and below the surface is in opposite directions. So that's our conclusion. So then we'll just, rather than call it hx top and hx bottom, let's just call both hx, but remember on the bottom that there's a negative sign. So now we can write our equation for current just in terms of hx. And this, what was a negative sign here, is now a positive sign because this negative canceled with that negative to give us a positive. So we now have an expression for total current in terms of the magnetic field. The other way we can arrive at total current is integrating the current density. Well, we know the current density in the plane is K. And so we have this current density all the way from A to B. That's a width of delta W. That means the total current has to be the Y component of K times this delta W. That should give us our total current. This is the second way to arrive at total current. Now what we can do is set our two answers equal. On the left here was our total current that we arrived at by integrating current density. And on the right is the total current that we arrived at by integrating the magnetic field around this closed loop that we're showing. So simplify this and we see that Ky is equal to 2hx. And we could write this as hx is 1/2 of Ky, but it's much more useful to write this in a vector form. So taking this conclusion and writing it in vector form, we end up with this. And we see that the magnetic field above this current is oriented in the x direction, and then below in the negative x direction. So the conclusion is the magnetic field is 1/2 of K times the surface normal. And the surface normal is pointing upward, so that when we're looking below, the fact that the surface normal is pointing upward and we will be calculating the field below, that's how it accounts for this reversal in direction. So there we arrive. We can calculate the magnetic field from a surface current. And to finish this, we're moving on to the volume current. The volume current is really the only current that actually physically exists. Everything else is a simplification of the volume current. So this is the only physically real one. And so when we talk about a volume current, we're looking at a cross section. Now our current density is written as J. This is the same J that appears in Maxwell's equations. It has units of amps per meter squared. So if we look at a little differential current element, that is our current density times our differential volume. So amps per meter squared for the current density times meters cubed gives us amp meters as the units for this little differential current element. That's the same units that our differential current element had for surface currents and the same units we had for our differential current for a line current. And so our equation to calculate the total magnetic field is a volume integral with the volume form of the Bio-Savart law. Let's apply what we've learned to figure out what the magnetic field is outside of a coaxial cable. So here we're showing a coaxial cable. It has an outer shell that's metallic. It has an inner fill that's some kind of permeable medium potentially, and an inner conductive core. We're going to let that inner core carry a current in this kind of lower left to upper right direction. So it's heading sort of into the screen, if you will. That means the outer conductor is carrying current in the opposite direction because this is a differential transmission line. Just as much current coming in has to come out. It's distributed over a larger area on the outside, but it's the same total current. Now we'll set up a closed line surrounding the coaxial cable. And remember what Ampere's circuit law says. If we do a line integral of the magnetic field around anything, the answer we get is the total current passing through that closed line. Well, we know that the total current that this is enclosing has to be zero because we have just as much current going from left to right as we do right to left. So total net current inside that. So the only way that we can get 0 from this line integral is if the magnetic field is also 0. So we conclude from this that the magnetic field outside of a coaxial cable has to be 0. That's our big conclusion. And when we analyzed this in electrostatics, we also saw that the electric field outside of a coaxial cable is 0. This is one of the magical things about a coaxial cable, in that it isolates the signal inside. Nothing can get in and nothing can get out. It's completely isolated. It's a very healthy, noise-immune way to propagate a signal.